Dr. Back, and today we're going to talk about molecular geometries. Now, it's going to be a shape that various molecules can take. And today you want to be able to predict the 15 geometries that can exist. Some of them overlap, so not quite 15, and you want to be able to estimate what is likely to be the approximate bond angles within those geometries. In chemistry, one of the major themes as you get into more advanced chemistry topics is going to be how the structure of chemistry relates to the function of chemistry. And all we're really doing in AP Chemistry is we're going to be learning about these 15 geometries, so learning about a little bit of the structure that these things should take, but it's a hugely important aspect for future chemistry classes. And this is a tremendous focus not only in chemistry classes, but in the chemistry world. So in drug discovery, there's a huge effort to be able to identify drugs, compounds to small molecules that will interact with proteins. And one of the ways to do this is to make a prediction about what drug molecule will be able to fit into some crevice or some enzyme. And one of my favorite examples of this is the HIV protease inhibitor that is called nelfinavir from a company called Agaron. And it looks something like this, a very complex molecule. But the way this was created, this molecule was built by looking at the three-dimensional structure of the protease. And this, in fact, is the active site was shown here in this red shadow, the active site of the protease enzyme. And this drug was designed to be able to fit tightly into that crevice and prevent the protease from functioning. And that's, in fact, what it does. So the protease inhibitor prevents the protease from cutting up the HIV polyprotein and inhibits the life cycle of the HIV virus. So this idea of a structure-based drug design is a huge effort in pharmaceutical companies, also sometimes called rational-based drug design. We're going to start learning about structures, and we're just going to learn about a few structures, but the idea is tremendously important. We're going to try to get down how to think about these structures and how to be able to make predictions based upon Lewis structures for what will be the three-dimensional shape and the space that these three-dimensional molecules will take up. Let's take a brief example. So here's boron trifluoride, and this is a boron molecule surrounded by 3 fluorine molecules. If we look at the three-dimensional structure of this, remember this is just a diagram. What's really happening is you have these clouds of electrons that are hanging out on the surfaces of these, in this case, the fluorine and boron molecules. And the principle that we're going to be using throughout the entire section today is that these clouds of electrons are going to arrange themselves to try to get away from each other. So if you think about the outside of these fluorine molecules, their electrons are negatively charged. So these negatively charged electrons are going to be trying to separate themselves from each other, get as far away from each other as they can. And so the molecule that forms looks something like this. Well, let's call this trigonal-planar. And so it has 3 atoms, and they have separated themselves as far away as they can get. And this happens to take this characteristic shape of being a plane of 3 different atoms that are separated from each other. So this is a basic concept. So we're going to be looking at how these molecules can arrange themselves so that their charges can be separated as much as possible from each other. That's the principle that we're going to come to. And the way we're going to start looking at this is by counting electron clouds. So electron clouds is an area where electrons are hanging out. So it can be a single bond, it can be a double bond as well, or a triple bond. Any type of bond, combination of bonds are going to be a place where a bunch of electrons are hanging out. We happen to have 2, 4, or 6 electrons hanging out in single, double, or triple bonds, but it still counts as a single electron cloud. We can also look at unbound pairs of electrons. So each pair of electrons will form its own cloud. Remember, they'll have opposite spins. And if for some odd reason you end up having a single electron, that will by itself make its own electron cloud. So each of these electron clouds will try to get away from each other. Okay, let's look at a model example here. So what we're going to be doing, we're going to be looking at central atoms, in this case the atom A, and we're going to be looking at the electron clouds that surround that atom. It doesn't matter, the B's could be connected to other atoms, it doesn't matter. All we're looking at is the geometry that's around the central atom A. In this case, we're going to have 2 single bonds. Each of those represents an electron cloud. So I have 2 clouds from those 2 single bonds. I have a double bond that double bond represents a single electron cloud. And I also have a pair of unbound electrons, also representing a single electron cloud. So in this atom, or surrounding A, I have a geometry that's going to consist of 4 electron clouds. Okay, and this is going to help me predict the structures. Okay, so not just atoms that we're looking for, but in general, electron clouds. Okay, and the way I like to look at this, a great simulation here from the PhET group. And what we're going to do is we're going to start adding in atoms to this, and then predicting what the geometry is going to be. So if I start with a central atom, doesn't matter what it is, it's purple. And I add 1 into this. So what is the geometry of this? This can only be one thing. It has to be a linear shape, so just 2 points. So I have a linear shape. If I add in a second atom, notice those 2 atoms now have arranged themselves to get as far away from each other as possible. Remember, on the surface of these atoms, there are clouds of electrons, and those clouds of electrons are negatively charged. They're just trying to get us away from each other as much as possible. And this is a dynamic process. This is not forced into this. It falls into this because that is the lowest energy state. They've repelled each other. They're getting as far away from each other as possible while still being connected by the sharing of electrons in that bond. So my molecular geometry is linear, and what I refer to my electron geometry is also linear. So I can keep adding in bonds, and now I have 3 atoms that are connected. They fall into this trigonal planar shape that we saw earlier. Okay, and the last one, which hopefully you've seen before, is when I have 4 that are connected together. And this is my tetrahedral shape. Looking at cloud charges, if you just have 1 cloud charge, you have a linear geometry. An example would be hydrogen fluoride. So there's 2 atoms that can only be in a linear arrangement. If I have 2 cloud charges, only 2 cloud charges, then it must also be linear. An example of this would be carbon dioxide. So we have a double bonds between the 2 carbon atoms, 2 oxygen atoms. And I'll end up having 2 cloud charges. And these will separate each other from each other as much as possible, end up with linear. Trigonal planar, where they have 3 cloud charges, an example of BF3, which saw before. Tetrahedral, an example would be methane, CH4, have 4 cloud charges. There are only 2 other ones that we need to know about. So these are the base shapes, and we're going to make it a little more complex, but these are the 6 base shapes. And if you get these 6 base shapes down, then you can decipher pretty much everything else that you need to know. So we're adding in 2 more. This time we're going to add in the trigonal, bipyramidal, and the octahedral. So we're just adding in 1 or 2 more additional atoms into our structure. So let's see what that looks like. So I'm just going to add in another atom here. And now I have something you may notice that runs up and down. So I have a linear relationship between these 2, my top and bottom ones in this case. And the 3 going around the middle have sort of a trigonal planar shape. So it's as if I've taken a trigonal planar shape and I've stuck one off the top and the bottom. These have fallen into this as being the easiest or the best way to get away from each other. So we can move it around, right? And the atoms continue to fall into the shape to get away from each other. So I have 5 terminal atoms in this case. 3 arranged around the center and 2 on the top and bottom. So we call it trigonal bipyramidal. So trigonal has got 3 around the center. Bipyramidal has got a pyramid on top and bottom. And lastly, I'm going to add 1 in here. And now I have a shape that we'll call octahedral. If these terminal atoms were vertices, I could end up having 8 facets. The reason it's called octahedral. It has 8 faces on the surface of this. And it's a natural arrangement. Again, all of these atoms are trying to get as far away from each other, and this is the best they can do. So I have 4 around the center and 1 coming out the top and bottom. Okay, these are the base shapes. These are the 6 base shapes. Right, 2 of them really trivial, right? So you have 2 linear shapes. We have trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And this is the sequence of having 1 to 6 cloud charges. Okay, this is the case where we've taken every single cloud charge consists of an atom. So it's connected to another atom. Octahedral, when I showed you SF6 would be an example. There are 6 fluorine atoms connected to the central sulfur atom. Doesn't have to be the case. So what we're going to do now is we're going to sort of add in or exchange one of the atoms for a separate cloud charge, which would be unpaired electrons. And we'll get slightly different shapes. So again, the shape of the molecule is going to be the shape the atoms take. The shape of the electron clouds, the electron geometry, is always going to be one of these 6. Okay, so let's take a look at what that looks like. Okay, here's my tetrahedral atom. Notice that the molecular geometry and the electron geometry are the same. So I have 4 cloud charges, and all 4 of these clouds are being represented by atoms themselves. I'm going to remove one of these bonds and replace it with a lone pair of electrons. Notice that my geometry for my electrons has not changed. I still have a tetrahedral shape. I still have 4 electron clouds, 4 clouds of charge floating around, and they're just trying to separate each other from as much as possible. I'll end up having a tetrahedral shape. However, the geometry of the molecule doesn't recognize or is influenced by those paired electrons. The geometry of the molecule is going to take a trigonal pyramidal shape, so it's no longer a flat trigonal planar. Those electrons are acting to repulse the atoms, and so I end up having this trigonal pyramidal shape. My electron geometry remains the same. If I remove another bound atom and replace it with an electron pair, I maintain the same geometry for electrons, so I still have a tetrahedral shape. Now I have a molecular biology, which is molecular geometry, which is a bent shape. And an example of this would be water. Water is going to have 2 electron clouds around the oxygen and bound to 2 hydrogen atoms. It's going to take this bent shape, which is characteristic. Okay, so I'm going to start here with my, I'll go back to here, my trigonal bipyramidal shape. So in this case, my trigonal is running up and down, and my linear arrangement is running left to right. So I'm going to remove one of these and add a lone pair. So here I have a lone pair of electrons. Notice that lone pair of electrons is behaving as if there was another atom there. That lone pair of electrons is behaving as if there's another atom there and is changing the shape, so the shape is remaining pretty close to what it was before. My electron geometry is still trigonal bipyramidal. The way my electrons are arranged, my electron clouds, I still have the same number of electron clouds, and they're arranged themselves in the same way to get away from each other as much as possible. However, now my molecular shape is different because I have 1 fewer atoms, and it takes what appears to be an odd shape, but the molecular shape now becomes what we call a seesaw shape. So a seesaw shape is going to be characteristic of having 5 electron clouds coming from only 4 atoms. So you can imagine there's a seesaw. I've tried to arrange this so you can imagine there's a seesaw. Here's a stand, and here's the bar that's going across it. So one of the atoms that's on the trigonal part of the trigonal bipyramidal shape has been replaced with an electron cloud. Okay. I can remove another bonding pair and replace that with another pair of electrons. In this case, my electron geometry remains the same. So I still have the same shape overall for electron clouds. I still have this pyramidal, this trigonal shape, with one coming out the top and the bottom. Now my molecular shape is much different though. So I just have fewer atoms to connect. And now I've ended up with this shape. I will call it, oh, there we go. There you go. I'll get it come around. So this is going to be called T-shaped for obvious reasons, shaped like a T. But notice that it has the same electron geometry, so the cloud charges are having the same influence. The only thing that's different is I have fewer models. And I can remove one last one, add a lone pair of electrons. And now my two atoms that are connected, trying to get as far away from each other as possible, I'll end up with a linear geometry, even though my electron geometry remains the same, trigonal, bipyramidal. And these are the 4 different shapes that are possible. So if all of my 5 cloud charges are bound atoms, then I have trigonal bipyramidal. If 4 are atoms and 1 is an electron cloud, unbound electron clouds, then I have a seesaw shape. If 2 are unbound electron clouds, I have a T shape. And if 3 out of the 5 are unbound electron clouds, then I have a linear shape. And some examples are given here. Okay. Lastly, let's look at the octahedral. So the octahedral, when I have 6 different electron clouds that surround my central atom, I can replace one of those with a pair of electrons, and I get a shape that has the same electron geometry, still an octahedral electron geometry, but the molecular geometry is now something we're going to call square pyramidal. So you can imagine a square coming off the bottom here and making a pyramid. So the shape of the molecule is going to be square pyramidal. My electron geometry remains octahedral. Notice the bond angles haven't changed. If I remove a bonding atom and replace that with a lone pair of electrons, it will arrange itself into this characteristic arrangement where I have my 2 electron pairs that are trying to get away from each other, that are on opposite sides of my central atom. And then my 4 connected atoms are arranged as much as possible away from each other. So again, my electron geometry remains the same. I have an octahedral, but my molecular geometry, structure of the atoms, is now a square planar. If I remove another atom and replace that with an electron pair, I will now get to a T shape. Notice we've seen this before. So we've seen T shape from the trigonal bipyramidal shape. It has only 2 electron clouds around the central atom. In this case, I have 3 electron clouds, but it generates the same molecular geometry. So I end up with a T shape with a different number of electron pairs. And if I continue to add these in, I'll get a linear shape from my octahedral shape where I have 4 electron pairs trying to get away from each other, and my 2 atoms also repelling each other to opposite sides of the central atom, making a linear shape. Again, electron geometry is octahedral. Okay. Okay, so these are the different shapes that the molecular geometries that I can come up with. If I have only 1 electron cloud, my molecular geometry has to be linear. If I have 2 electron clouds, my molecular geometry has to be linear. If I have 3 electron clouds, if I have 3 bound atoms, it will be trigonal planar. If I only have 2 bound atoms, it will be bent. If I have 4 electron clouds, if all 4 of those are bound atoms, I have tetrahedral. If 3 of those are bound atoms, I'll have trigonal pyramidal. If 2 of those are bound atoms, then I have a bent structure similar to water. If I have 5 electron clouds bound to 5 atoms, that'll be a trigonal bipyramidal. If it's bound to 4 atoms, it'll be a seesaw. 3 atoms will be T-shaped. 2 atoms will be linear. And if I have 6 electron clouds bound to 6 atoms, The molecular geometry is going to be octahedral, 5 square pyramidal, 4 square planar, 3 T-shape, 2 linear, and short. Notice of the 15 geometries that there are some repeats, right? So there are several different ways to have a linear molecule. And there are different ways to get T-shaped. So T-shape can be generated through either the trigonal bipyramidal electron structure or the octahedral electron structure. Last thing you want to be able to do is to predict the bond angles. So we're going to base these bond angles off of ideals and then make a little tweak on this. So in a linear molecule, my bond angle is pretty straightforward. So if I have 2 atoms either side, I'm going to have a bond angle of 180. My trigonal planar, my 3 atoms are trying to get as far away from each other, all on the same plane. They'll be 120 degrees away from each other. Interesting thing happens when I go to my bent atom from my trigonal planar. So let's go to, this is electron geometry, which is trigonal planar. And my bent angle between these 2 atoms is shown here as well. Nice little molecular geometry. So the question is, what's the angle here? If this was, if my molecular geometry was trigonal planar, I would have 120 degrees. Notice my electron cloud, in this case, is shown as being closer to the central atom than my 2 other atoms. So in these electron clouds being physically closer to the central atom will act to repel a little bit more than an individual atom would. So my bond angle is going to be a little bit different. So instead of being 120 degrees, it's going to be a little bit less than 120 degrees. I'm not going to worry about how much less, but it's important to recognize that there is a distinction between something which is trigonal planar, the bond angle will be exactly 120 degrees, and when something is bent with a trigonal planar electron cloud structure, but is a bent molecular geometry, that angle is going to be less than 120 degrees. Okay. Same thing happens for tetrahedral. So notice here, here's my tetrahedral electron geometry. My bond angles, the most distance, the best distance that can separate from each other is going to be 109.5 degrees. Okay. When I replace one of these with a lone pair, that lone pair of electrons acts to draw those in a little bit, to push those atoms a little bit more towards each other, more away from the unbound electrons, and I'll end up having an angle which is less than 109.5. And similarly, if I remove another one, I'll end up having my bent structure. Notice my bent structure here is going to have a different bond angle. This is going to be a little bit less than 109.5. Here's the bond angle from my bent structure based off of the trigonal pyramidal. It's going to be less than 120. So we have the same molecular shape. The bond angles will be different based upon the number of cloud charts. Okay, so I'm going to go to the trigonal bipyramidal. Here, notice I have 2 different bond angles. The bond angles between each of my trigonal going around the center. The bond angle there is going to be 120 degrees. The bond angle between the 2 poking up and down and the trigonal ones around the center is going to be 90 degrees. Right? So I have 2 different bond angles here, 120 degrees or 90 degrees. If I replace one of these, notice it replaced one of the trigonal ones around the center. So this is the natural tendency that it'll fall into. Again, I'll have a seesaw shape, a trigonal bipyramidal electron structure. So the molecular geometry is going to be seesaw. This will act to change the bond angles, it'll be a little bit less than 120 degrees. Notice my 180 degrees remains pretty close to 180 degrees. If I remove another one, I end up with a T-shape. Notice the bond angle between the T-shape. This will be 90 degrees, not affected by the competing electron clouds from non-bound electrons. Okay, lastly, let's take a look at the octahedral. Here's my octahedral. Angle between any of these is going to be 90 degrees. I'll have 90 degrees between any of my atoms. If I replace one with a lone pair of electrons, end up with similar bond angles. If I replace it with two unbound electrons, see my square planar, those electron clouds are offsetting each other, so the bond angles will still be 90 degrees. If I add a third one in, I get to a T structure. Again, the electron clouds are repelling each other, not affecting the bond angles. End up with 90-degree bond angles. And of course, we end up with a linear, still 180 degrees. Okay, let's try a few practice problems. So here I'm going to take sulfur tetrachloride. So the first thing I'm going to do, I'm going to make the Lewis structure for this. And from the Lewis structure, I'm going to count what are the bonds and the unbound electron. So I have 4 bonds and 1 unbound electron. So I have 5 electron clouds. So I have 5 charges. So the electron structure is going to be trigonal bipyramidal. Notice I have 4 bound atoms. So I'll end up having a seesaw shape. My molecular geometry will be seesaw. My electron structure will be trigonal bipyramidal. Second example, we'll look at ClF3, chlorine trifluoride. We'll draw the Lewis structure for this first. So we'll have a chlorine bound to 3 fluorine molecules, and we'll end up with 2 pairs of unbound electrons on that chlorine atom. So I have 5 electron clouds and 3 bound atoms. 5 electron clouds means electron geometry is going to be trigonal bipyramidal. I have 3 bound in there. I will have a T-shaped molecular geometry from this. And lastly, we'll look at BRF5. I'll draw the Lewis structure for this, and I'll have something that looks like this. I'll have my bromine with 5 fluorine molecules, 5 fluorine atoms surrounding it. The single pair of unbound electrons around my bromine. Altogether, I have 6 electron clouds. This will take an octahedral electron structure with only 1 unbound pair of electrons and 5 bound electrons. I'll have square pyramidal will be the molecular geometry. Okay, so you have 15 different structures to identify. My recommendation is use the base patterns. So think about how many electron clouds there are, figure out the electron geometry first, and then work your way to what the molecular geometry might be from that. So there are 5 base patterns: linear, trigonal, planar, tetrahedral, which you've seen before, 2 new ones, trigonal, bipyramidal, and octahedral. Tetrahedral, of course, has 4 atoms, 4 electron clouds. Trigonal bipyramidal has 5, and octahedral has 6. And lastly, when you estimate the bond angle, account for the unbound electrons. Thank you.